Welcome to EDU World Space.
All right, so we have the following molecule. And the question is, what is the splitting pattern we expect in an H&MR signal for the proton, which I will circle here. And your thought, it appears, was a doublet of doublets. It's a right idea, right? We are supposed to consider long-range splitting. And so if you look at potential long-range splitting for this particular proton, we'll see that, well, we should expect to be split here. And likewise, we should expect to be split here. So we're going to get split twice, right? We've got two sets of neighboring hydrogens. Maybe to make things a little more clear, we'll redraw this molecule so that you can see that, remember, this is a methyl group, which means there's three hydrogens sticking off of here. Okay, right, so one of the splittings will come from 1, 2, 3 bonds away in that manner, but will also be split 1, 2, 3 in that manner by these three hydrogens, right? So we're going to be split 3 ways and then split once more. And then there'll be no long-range splitting here, and then this is too far away. Okay, so the next question you need to answer then is how large, right, is the coupling constant for these various splittings that we're going to see. Recall that hydrogens, which are trans to each other across a double bond, actually have a very significantly large coupling constant. They are, trans protons, vicinal trans protons, have a splitting constant of around 11 to 18, depending, right? And then in the case of this splitting over here with the methyl group, there's actually not a special relationship or name for this kind of splitting or coupling, right? It's actually pretty much the exact same situation as, say, any proton which neighbors a methyl group, right? So you expect splitting to be on the order of your typical splitting constants for hydrogens on a neighboring carbon, somewhere between 4 and 10. Okay, and this is in Hertz, right? And so recall that when we decide whether, if we've got, for example, a neighbor of 3, which will split us into a quartet, and a neighbor of 1, which will split us into a doublet, we end up having, say, either a quartet of doublets or a doublet of quartets. And the way we decide how to label this is that we list them in order of the size of the corresponding splitting constants, right? So this trans relationship and splitting pattern from these two protons has a coupling constant between 11 and 18, right? Whereas the standard one here has a coupling constant that's in the range of 4 to 10. So really the doublet pattern should be the sort of first thing we list, and the quartet we get from neighboring 3 protons should be the second thing we list. So when deciding between whether this is a doublet of quartet or a quartet of doublets, here we would label it as a doublet of quartets. Okay, so this is going to be answer E, doublet of quartets. It looks like you had the right idea. You just maybe didn't realize this was a CH3, so it should be quartet rather than doublet. Remember, n plus 1, n equals 3, which implies that we would get 4 signals, which corresponds to a quartet. Here, n equals 1, right, which would imply 2 signals, which we call a doublet.